Hello, I'm Kirk Weiler, and this is Common Core Algebra 2 by eMath Instruction. Today, we're going to be looking at Unit number 11, Lesson number 3 on the unit circle. The unit circle is probably the most important geometric device that we're going to be seeing, or the most important geometric object that we're going to see in this unit. Primarily because the functions, known as the trig functions, are based on its geometry. So let's jump in and just kind of understand what the unit circle is. It's a pretty easy idea. The unit circle is a circle that's centered at the origin. It's got its center right at the origin and has a radius of 1. And because it's centered at the origin with a radius of 1, then you get points on it like 1 unit to the right, 1 unit to the left, 1 unit above, 1 unit below. All right? Now, a question from Common Core geometry. From our work with equations of circles, which of the following would represent the equation of the unit circle? See which one of those things strikes you as being the equation of the unit circle. All right. Well, hopefully you said choice 3. All right. Now, you may remember things about circles from Common Core geometry. You may not. So let me just review something really quick. The reason that this is the equation of this circle is very simple. If we were to draw in this right triangle with this coordinate pair x, y, well then obviously this is x. That's just what the x coordinate is. It's the distance from the y-axis. And this coordinate is y, again for the same reason. But that means the three sides of this right triangle can be related by the Pythagorean theorem. A squared plus b squared equals c squared. Well, but a is x, so that would be x squared plus y squared is equal to the hypotenuse squared. So that means we have x squared plus y squared is equal to 1. That's the equation of that circle. Now that isn't just some like little trivia question. X squared plus y squared equals 1 is going to be an amazingly important thing even in the next exercise. So pause the video now and make sure you understand this idea. Okay, let me clear out the text. All right. Let's jump in and do a little bit of Pythagorean theorem work. All right, now back in geometry, Common Core geometry, you did learn, or you were supposed to learn, about what were known as the special right triangles, but we're going to review that right here. Exercise 2 says, consider a right triangle shown whose hypotenuse is equal to 1 and both sides are equal, and whose angles are both equal to 45. This is an isosceles right triangle, which means that the two sides, the two legs, have the same length. So I'm going to call them both x. It says solve for x and place your answer in simplest radical form. Let's do this together. As we just reviewed, all side lengths on a right triangle can be related by the Pythagorean theorem. In this case, two of the side lengths are x, and one of the side lengths is 1. So we just get 2x squared is equal to 1. Obviously, I can now solve by dividing both sides by 2, and I'll get x squared equals 1/2. I'll take the square root. Now, typically I should introduce a plus minus right now, but I'm not going to because it's a length and therefore it can only be positive. Now, x really is the square root of 1/2, but that's not considered simplest radical form for a bunch of different reasons. Reason number 1 is that we can apply the square root to both the numerator and the denominator. Now, the numerator is nice. The square root of 1 is 1, but the square root of 2 I have to leave alone. Now, I'm really happy with 1 divided by the square root of 2 right now. But oftentimes, people take this one further step and they do what's known as rationalizing the denominator. You don't need to know that term particularly. It just means I'm going to multiply top and bottom by root 2. And the reason I do that is root 2 times 1 is root 2. And root 2 times root 2, as we should all know, is 2. So this tends to be the final answer. Now, what does that mean? Now, this is going to be important for later. If we have a right triangle that's a 45-45 right triangle, and its hypotenuse is 1, then the two legs have length the square root of 2 divided by 2. All right, so this triangle is going to be important for us in a little while. But for right now, pause the video, think about what we did, and then we'll move on to a 30-60 right triangle. Okay, great. Clear this out. Let's take a look at a 30-60 right triangle. Now, a 30-60 right triangle is 1/2 of an equilateral triangle. I want you to make sure you understand this. This is important. Right, an equilateral triangle, one where all the sides are the same length, okay, as we all know from geometry, has angles of 60 degrees everywhere. So if I slice it in half, that gives me the 30-60 right triangle. So we now have let's say we have an equilateral triangle, all of whose side lengths are equal to 1. Well, what would be the length of the shorter side? This one. Think about that for a moment. Did you figure it out? It's got to be 1/2, right? I mean, it's just half of an equilateral triangle. So the length of the shorter side has to be 1/2. Now it says use the Pythagorean Theorem to find the other side. Let me call that b. All right, so we just got to be careful, right? We know a squared plus b squared is equal to c squared. So I'll let my a be equal to 1/2 squared. B is what I'm looking for. And then my c is again 1 here. You'll understand eventually why I keep making my c 1. 1/2 squared is 1/4 plus b squared is equal to 1. I'll just get rid of a 1/4 from both sides. That's going to leave me with b squared is equal to 3/4. And now I'll take the square root of both sides. So b is equal to the square root of 3/4. Now, just like before, I wish we could leave it like that, but the tendency is that we break it up as the square root of 3 divided by the square root of 4. Now, the only reason we're doing that is that even though the square root of 3 is an irrational number, the square root of 4 can easily be found, and that's 2. So that is root 3 divided by 2. We don't have to do that little trick we did last time where we multiplied top and bottom. No problem having a square root in the top, but classically, square roots are not typically left in denominators of fractions. It's acceptable. It used to be completely unacceptable. Now it's all right, but this is more conventional. So again, we're going to be dealing with this triangle soon, a 30-60 right triangle, where the hypotenuse is 1, the shorter side is 1/2, and the longer side is square root of 3 divided by 2. Okay? So, pause the video now, take a look at this, and then we're going to play around with the unit circle. Okay, clear out the text. Oh my goodness. All right, so I have a unit circle. This is a circle whose length is 1, okay, or whose radius is 1. I shouldn't say its length is 1. So a circle whose radius is 1. And I have a bunch of really important angles marked off on this circle. And they're marked off from standard position. In other words, a counterclockwise rotation is positive. We could go clockwise and mark off negative angles as well, but I just went counterclockwise. All of these angles are either multiples of 90, like 0, 90, 180, 270, or they're multiples of 30, like 30, 60, 90, 120, 150, 180, 210, 240, or they're multiples of 45. These are a little bit trickier to think about. 0, 45, 90, 135, 225, 270, 315, and back to 360. All right? What we want to do is fill in all the coordinates of these points on the circle, the coordinates. Now, one of them is really easy. Let's start down here. That's simple. That's going to be the coordinate point 1, 0. Why don't we do all the easy ones? 90 is going to be the point 0, 1. 180 is going to be the point -1, 0. And 270 is going to be the point 0, -1. Those are all easy because the radius is equal to 1, and they lie on either the y or the x-axis, so piece of cake. Now, here's where it gets a little bit more difficult. And I'm I'm going to draw out those two triangles that we had before. We had one triangle, that 45, 45 triangle. I'm not going to put the other one in there, which had 1 here, and square root of 2 divided by 2, and square root of 2 divided by 2. That was one of them. And the other one was that 30, 60 triangle. This time I want to put the 30 and the 60, where there was a 1 there, a 1/2 there, and a square root of 3 divided by 2 there. All right, so let's take a look at this triangle. Now that's a 30, 60 triangle, with this being 30, this being 60, and this being a length of 1. That means we're going to look at this thing. Now this is the longer side, so it's got that square root of 3 divided by 2 length, and this is the shorter side, and it's got a length of 1/2, right? It's across from the 30, that's across from the 60. Therefore, the coordinates at 30 degrees are an x-coordinate of root 3 divided by 2 and a y-coordinate of 1/2. Now, I'd like to pause for a moment because I'd like to eventually erase all of this stuff in here. I'd like to pause for a moment and have you think about where that coordinate point came from. All right, well, I'm going to erase that. Let's go with a medium eraser just so that we have a little bit more room. All right, now let's take a look at the next angle at 45 degrees. Well, that thing is coming from this right triangle, right? But that right triangle is this 45, 45 right triangle, right? It's exactly that triangle because it's got a hypotenuse of 1, which means this length must be root 2 over 2, and this length must be root 2 over 2. So the coordinate point for 45 degrees has to be root 2 over 2, comma, root 2 over 2. Okay, just the side lengths of this triangle. Think about that again, because I'm going to erase some of this stuff down here. Okay, let me get rid of it. All right, this is going to speed up eventually, I promise. Now, let's take a look at this one, the 60-degree angle. The 60-degree angle is being formed, or is helping to form, this right triangle. Now, this is a right triangle whose base angle here is 60 degrees, which means this has got to be 30 degrees. This has got a length of 1, the hypotenuse, so that means we're back to this triangle again. But unlike the 30 degrees situation, this is now 1/2, and this is root 3 over 2. So the coordinate point for 60 degrees is 1/2 root 3 over 2. It's exactly the same as this coordinate point, but with the x and the y coordinates flipped. Again, let me step back, pause for a minute, because after this we're going to really start to speed it up. So pause the video for a minute and think about what we just did. Okay. Get rid of this. That's one big eraser. Put this back in. All right. Now, let's go to the second quadrant. How do we find the coordinate point for 120? Well, this point is just a reflection of this one across the y-axis. So when we do that, the x-coordinate becomes negated, but the y-coordinate remains the same. See that? Likewise, the 135 degrees is just a reflection of this point across the y-axis, so the x-coordinate gets negated and the y-coordinate stays the same. And same song, third verse. The 150 is a reflection of the 30, so the x-coordinate gets negated and the y-coordinate stays the same. That's it, right? Wow, we just did the second quadrant like that. That was a piece of cake. All right, let me get rid of these dashed lines for a moment, because here comes the third quadrant. The third quadrant is going to be easy too. because this point down here is a reflection of this point across the x-axis, which means its x-coordinate should stay the same, but its y-coordinate gets negated. This point is a reflection of this one across the x-axis, so yet again, x-coordinate stays the same, y-coordinate gets negated. And finally, same thing here. For 240, that's the 120 reflected across the x-axis. So the x-coordinate remains the same. The y-coordinate gets negated. I think I'll leave those lines on here because to get all these fourth quadrant angles, we can reflect the first quadrant angles in the x-axis, so that root 3 over 2 1/2 would then become a root 3 over 2 comma negative 1/2. This one will get reflected. 315 will be root 2 over 2 comma negative root 2 over 2. And when we reflect this, we would get 1/2 comma negative root 3 over 2. Now, a driving question that should be in every student's head right now is, why in the world are we doing this? Why are we doing this? Now, that's a little bit tricky. These coordinate pairs are what are called the special angles, okay? And they're pretty much only special because we can find the exact coordinate pairs. Don't get me wrong, an angle of 72 degrees, which isn't on here, 72 degrees, is very important. But we can't actually come up with the exact coordinate pair that lies on this circle. So that's one thing. The other thing is that all of these coordinate pairs, as well as just the unit circle in general, is going to become very, very important for us when we start to work with what are called the trig functions in the next unit. Now, those trig functions you've seen already in geometry. And in the next lesson, we're going to rethink about the sine and the cosine functions, okay? But once we get there in the next lesson, then the unit circle and all of this work will make a lot more sense. Anyhow, pause the video now, write down anything you need to, and then we'll do the last problem. Okay, I'm going to clear out the text. Thankfully, I'm not going to redo that diagram every time. There it is. Okay, I know it's a little bit smaller, but hopefully you can see it on whatever screen you're watching this video on. Okay, it's got all those coordinate pairs. Now, exercise 4 says, for each of the following angles drawn in standard position, give the coordinate pair from the unit circle. All right, so I'm not going to say, hey, 135 degrees, because you'll just look at the unit circle and say, there it is. All right, but how about negative 120 degrees? If I drew that in, right, negative 120 degrees would be coterminal with positive 240 degrees. All right, it would be coterminal with it. All right, think about that. All right, and therefore, the coordinate pair that goes with it is negative 1/2 negative root 3 over 2. So the point is, if the angle that we want to know about is not on that diagram, we have to figure out if it's coterminal with an angle that is on that diagram. So think about that for 495 degrees. All right, well, 495 degrees is more than one full rotation. So based on a couple lessons ago, if we want to figure out what it's coterminal with, we can just subtract off 360. But that makes it coterminal with 135 degrees, which means the coordinate pair is negative root 2 over 2, comma, positive root 2 over 2. Oh, and letter C and letter D are radian angles, right? Now, we were supposed to get much better at those in homework last night. But if you don't remember what pi over 3 is, and I hope you do, it was one of the ones that I said, this is an angle you want to know. All right, then you can do your conversion, right? By multiplying by pi, by 180 degrees divided by pi, right? The radians would cancel radians, and pi would cancel pi. 180 divided by 3 is 60 degrees. It's not a coterminal angle. That's actually the exact angle. So we'd have 1/2 root 3 over 2. All right, why don't you try to do letter D? All right, 3 pi over 2, one of the most important angles of all, but again, if you don't remember what it's equal to, work on that because it's a very important one. All right, radians cancel, pi's cancel, 2 goes into 180 90 times, and 3 times 90 is a 270. And there we're at 0, -1. All right, so get used to that unit diagram. Unit circle diagram, it's going to be needed, very necessary. All right, keep that handy, especially in the next couple lessons. We're going to want it. All right, but pause the video now, write down anything you need to, then we'll wrap it up. Okay, I'm going to clear out the text. All right, all of trigonometry will eventually be based on this thing called the unit circle. A circle whose center is at the origin and whose radius is exactly 1 unit long. In the next lesson, we'll see how we can define the sine and the cosine functions, not just using those right triangle trig ratios from last year, but using this unit circle as well. That will allow us to have the sine and the cosine of any angle, positive, negative, bigger than 90, less than 90, etc. All right. Well, thank you for joining me for another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.